Okay, so in any plane where x equals constant, you just have y and z to worry about, and it's clear that y squared plus z squared is 1, right? And that should be familiar to you from parameterizing curves. Circles are some of the easiest things to parameterize, right? If I put a coefficient on this, make it an ellipse, well then that's going to affect your derivatives here, right? And you're not going to have such a simple result. And your integral might end up being a lot less simple, okay? So you can think about what that would do, but we have z squared plus y squared is a cosine squared of v plus a sine squared of v, which is 1, okay? Circle of radius 1, right? And well, I won't say what its centered arc is yet. Circle of radius 1. Now, x equals u squared, right? So it makes you think of a parabola. That's not quite right because in the xz plane, you have z equals cosine v, okay? And you have x equals u squared, where u goes from 0 to v. So if v equals 0, then u has to be 0, right? So let's just look in the xz plane, okay? For v equals 0, we have only this point. Okay? Now for v equals 2 pi, oh, wait a minute, whoa. Yeah, for v equals 0, z is a cosine of v, right? Cosine is 1, so I was wrong about that. Okay. So z equals 1, x equals 0. So the v equals 0 point is just a point here, okay? Now for v equals let's say pi, z is -1, and x goes, well, u goes from 0 to pi, right? So x goes from 0 to pi squared. So v equals pi. We have negative 1 down here. Okay, so this would be the point 1, 0. This would be the point, sorry, 0, 1. This would be the point 0, negative 1. And x would go from 0 to pi squared. So you have all these x values out here to pi squared. Okay? That's a little weird. Okay? For v equals pi over 2, z would be 0. And x is going to go from 0 to pi squared over 4. Okay? So, if this is pi squared, then pi squared over 4 is here. So you have this region. As v goes from 0 to pi, I'm not talking about 2 pi because we can visualize what's going to happen there. Okay? As v goes from 0 to pi, z is going to go from 1 to negative 1, right? And x is going to go from 0 to v squared. So, when v is 0, x just has to be 0. When v equals pi, we go from 0 to pi squared, right? And we're going to have a curve that looks something like this. Now, as we continue on, we end up with a complication, but maybe not. As we go from pi to 2 pi, our z values are going to go from here back to here. Okay? But our maximum x values are going to do something quite a bit more complicated. They're going to continue going up to 4 pi squared, so it's going to come way out here, and you're going to have a curve that looks like this, and now you're going to have this stuff superimposed on this. Now, in the meantime, what's y doing? It's doing something very similar, but now when v is 0, you're at 1, right? And then you go up here and back down here, back down to here and up to here. And you have a similar surface here, and then you try to put that all together and visualize the thing, and it's a little bit complicated, okay? But whatever that surface is, whatever it looks like, and you can kind of think about it a little bit because we're out of time, this is going to be its area, okay? Because of everything we've developed. So I recommend you look at examples, look at different parameterizations. They're all simpler than this one. I chose this one not because the surface is easy to see. The surface is pretty hard to see, okay? But the integral is really simple. So it's a kind of weird, complicated surface that you would have a lot of trouble doing in x, y, z coordinates, but that you do rather easily in UV coordinates. Okay? Now again, you want to think of this, in the first place, you have circles of radius 1 here in the UV plane. So what surface are you getting? You're restricted to that cylinder.
So this will get you the surface area of your